All right, today we're tackling a problem that is quite literally microscopic. We're going to talk about building the future of electronics with wires that are just a few atoms wide. And you're going to love this. The secret tool to make it all work? It's hidden in the blueprint of life itself.
So first up, let's meet our main character, the carbon nanotube. These things are, and I'm not exaggerating, the stuff of science fiction. They're basically rolled up sheets of graphene, and their properties, just incredible. They're stronger than steel, and they conduct electricity better than copper. In fact, electrons can just fly right through them with almost zero resistance. They are, in theory, the perfect wire.
You can see why everyone's so excited, right? These could completely change computers, medicine, you name it. But, and it's a huge but, there's a massive roadblock. The moment you try to connect these perfect little nanowires to our clunky, regular-sized world, well, that's when it all falls apart.
And that's really the heart of the issue here. The problem isn't the nanotube itself, it's the connection point. How in the world do you build something reliably when the pieces are so small you can't even see them? It's an engineering challenge on a scale that is just mind-boggling.
Okay, let's really dig into this roadblock. The problem boils down to something scientists call contact resistance. Think of it like a huge electrical pothole right at the spot where a normal metal wire is supposed to touch the tiny carbon nanotube. So the dream, the promise, is this beautiful, clean connection with a resistance of about 6.25 kiloohms, which is incredibly low. But the reality? It's more like a massive traffic jam. That one tiny, imperfect connection point creates so much resistance that it just chokes the whole system, completely preventing these amazing devices from ever reaching their full potential. And just how bad is it? Get this, the actual resistance scientists were measuring was all over the place. It could be 10,000 ohms, or it could be 1,000,000,000 ohms. That's a range of 100,000 times. I mean, how can you build reliable electronics when your components are that unpredictable? You just can't. So, if you've got a nanoscale construction problem, you need a nanoscale construction tool. And the scientists on this project found one in, honestly, the last place you might look. Not in a physics lab, but in a biology lab. They turned to DNA. Seriously, just think about it for a second. You need to place tiny metal particles with perfect precision along a wire that's itself almost impossibly small. You can't use tweezers, you can't build a tiny robot to do it, so what do? Use the one molecule that has been building complex, intricate machinery with atomic precision for billions of years. The researchers had this incredible idea, what if DNA could be the ultimate template for building their nanocircuits? And it turns out DNA is perfect for this. It does two absolutely critical jobs. First, carbon nanotubes are super sticky. They just love to clump together. So the DNA acts like a crowd controller. It wraps itself around each nanotube, and its natural negative charge creates this kind of force field that pushes them all apart. Job one, done. But second, and this is the genius part, that same negative charge acts as the perfect construction scaffold, attracting positively charged metal ions to come and stick right where the scientists need them. So, how did they actually pull this off? Well, the team came up with a surprisingly simple, almost elegant chemical recipe to turn this theory into a real thing. It's basically a three-step process to build a whole new kind of hybrid wire. First, you take your nanotubes and you mix them into a solution with the DNA. You blast them with sound waves and spin them in a centrifuge just to make sure that DNA wraps itself nice and snug around the tubes. Then, you add a solution full of positively charged platinum ions, and you wait. For 24 hours, you just let it sit while those platinum ions get drawn in and stick to the negatively charged DNA. Finally, you add one last chemical. This kicks off a reaction, and boom, those platinum ions lock into place, forming tiny, perfect, solid crystals. The recipe sounds great, right? But this is science. You have to prove it. Did it actually work? To find out, the team had to look. And for that, they needed an incredibly powerful transmission electron microscope to see what they'd made. So the first thing they saw? Success! The DNA had done its job as a crowd controller perfectly. The nanotubes, which usually look like a big clumpy mess, were all beautifully separated into individual strands. Step one, nailed it. But here's where it gets really, really cool. The images also showed these tiny little dots, just 1 or 2 nanometers across, all along the strands. Those were the platinum nanoparticles. And they weren't just stuck on there randomly. No, they had formed with incredible precision right along the DNA molecules. In the researchers' own words, and I think this says it all, The PT nanoparticles were single crystals attached to the DNA molecules rather than to the nanotubes. This was the smoking gun. The DNA had worked. It acted as the perfect template, guiding the construction exactly as planned. You see, what this proves isn't just a new trick for making one tiny wire. It's a proof of concept for a completely new way of building things at the nanoscale. It's about hijacking the elegant machinery of biology to solve the toughest problems in electronics. So what we're left with is this amazing, beautiful hybrid material. You've got the carbon nanotube at the core. That's our perfect wire. You've got the DNA wrapped around it, doing double duty as a separator and a construction guide. And then, decorating the DNA, you have these platinum nanoparticles, creating what the researchers hope will be the perfect conducting channel to finally solve that pesky resistance problem. And that's the big takeaway from the team themselves. They called this a promising technique for producing nanoparticles with controlled configurations, which basically opens up a whole new toolbox for creating the next wave of nanoscale electronics.
I just find this so fascinating. This experiment is this brilliant marriage of material science and molecular biology. It shows that the elegant, self-assembling systems that life has spent billions of years perfecting can be borrowed, can be repurposed to build our future. It just leaves you wondering, what other secrets is biology holding that are just waiting to help us build the world of tomorrow?